Welcome to diffraction. We're going to look at single slit diffraction and then diffraction gratings. So we've previously talked about diffraction and how the gap and its relation to the wavelength can affect the amount of diffraction. And I've got some screenshots from the PhET simulation here to show this effect. So we've talked about it in very simple terms previously. The idea being that when the gap is very, very wide, you get diffraction happening, but the angle of that diffraction is not very large. When the gap is equal to the wavelength of the wave, and I've got the wavelength set to 500 nanometers, and I've got this gap set to a width of 500 nanometers, you get the maximum angle of diffraction, and you get these spherical wavefronts. We've previously talked about what happens if you make this gap even smaller and the wave being blocked. This actually happens very gradually. So you can make the gap smaller and smaller and smaller. And what happens is that the intensity, and that's what this graph shows here on the right-hand side, you can see that the intensity falls off. So where the gap is equal to the wavelength, you have this intensity graph, and when the gap is about half the size of the wavelength, you have very low intensity indeed, and that just keeps falling off until eventually the wave has zero intensity on the other side. And this is one of the reasons why microwave ovens are designed with a mesh in the door, so that when you look through the glass into the inside of the microwave oven, the visible light is able to escape and you can see the food that's cooking, but the microwaves that are cooking the food are not able to escape because the size of the holes in the mesh are much, much, much smaller than the wavelength. So the intensity of the microwaves that can escape is so low that they're not harmful to anybody. You may notice in this example up here where the gap is much, much larger than the wavelength, where the gap is much, much larger than the wavelength, you're getting an unusual pattern. And this pattern of intensity, which falls off the edge of the screen, has these shoulders. Now, this PhET simulation doesn't allow me to go any deeper into this, but I do have another simulation that I can show you. So the PhET simulation is limited because in that simulation you cannot increase the width of the gap by many, many, many times larger than the wavelength, but this simulation does let you do that. So what we have is we have our ray of light landing across a single slit, and then the light coming through the other side and landing on a screen. The graph of intensity down here at the bottom, you'll notice, is the angle of that light. So at the minute we have a light ray that's coming straight through and it's not being diverted through any angle. So we have one dot here at the 0 degrees. Now what I've got here is I've got red light, and I'm going to work my way through the spectrum. We're going to look at red and orange and green and blue and purple light, and I'm going to be able to alter the width of the slit. And I've got a much wider range here in this simulation than I do in the PhET simulation. So I'll be able to show you this effect much more easily. So if we start off with red and we have a slit this size, we get this kind of pattern. We get an intensity graph that we have previously seen. If I increase the width of the slit, then you will start to see something called single slit diffraction, and that's where the different parts of the wave going through the extreme left and the extreme right side of the slit start to interfere with each other. We'll look at that in greater detail in a minute, but we're going to look at the pattern of the width of the slit and the wavelength for now. So if I increase the width of the slit, then we start to see a diffraction pattern, and we can see the central fringe over here, and then we can start to see those shoulders that the PhET simulation was only hinting at previously. Let's make it even wider. See, already we're much wider than the PhET simulation allowed us to go. And these shoulders are starting to turn into other fringes. And that's what we get if we get a bigger and bigger and bigger slit. So we're starting to see these different intensities of light. And if I move the angle, then you can see where we are. And I'll move that to the next fringe. And you can see that these fringes here, so this is n equals 0, this is n equals 1. That's where we're getting those little shoulders of a higher intensity. And that's what the rest of these are as well. If we increase it, that's what's happening. So when we go from a narrow slit to a wide slit, we are making the central maxima much narrower, and we are getting additional fringes introduced as well. Let's have a look and see what happens with the other colours. So we've got, let's have like a yellow colour, make the width bigger, and we get the same pattern happening. The bigger the width, the narrower the central fringe, and the more fringes you get. A green light, making that width bigger and bigger and bigger, you get the same pattern again. And then let's finally go to sort of bluey purple light. And again, if we make the width of the slit bigger, we get that same behavior. What you may notice, and what I hope you notice, is that the width of that central maxima is different for the different colours at different widths. So what we're going to do now is we're going to set the width, and we're going to keep that still, and we're just going to change the wavelength. So let's go back to red light, which is over here roughly. And you should notice that if I change the colour, then the amount of diffraction that occurs with that wavelength is different for different wavelengths. So here we have red, yellow, narrower, green, again a narrower central fringe, blue, narrower still, and then finally purple, that's the narrowest. We go back to red and we put the width of the slit somewhere in the middle like this. We're having a look at the separation of these fringes now. So watch this graph down at the bottom and you should see the pattern. So red, we decrease the wavelength and we are decreasing the width of the fringes. Let's decrease the wavelength again to green and we get narrower fringes again. Blue, very narrow, and finally purple. These are the narrowest that this simulation will allow. So the pattern is that as the wavelength decreases, the width of the fringes decreases. And the other pattern is the width of the slit. As the width of the slit increases, the width of the fringes decreases. Okay, so we've been having a look at this situation here where we've got a very, very wide slit and the waves that are approaching have a narrow wavelength compared to that slit. And you do get diffraction occurring, but it's like this, where it's just on the edges. Now what's really going on is that every single location in this gap is a source of spherical waveforms. And when they superimpose, when they interfere with each other, we get this pattern here. But what we can also think is happening, let's draw on the screen, is we can also think that this location here is sending out waves and they are arriving at the screen. And this position here is sending out waves as well, and they are also arriving at that point in the screen. So all of these individual points, and there are an infinite number of them, filling up every single little space. They are all sources of spherical waves. Now, you don't need to study this in a huge amount of detail, but you do need to know that a very, very wide gap is capable of producing an interference pattern. And this is shown a little bit in the PhET simulation, but it's shown very well in the simulation that I've just gone through with you. So what we end up with is an interference pattern from a single slit. And that interference pattern has a central fringe, and it has other fringes as well, just like with a double slit. So what happens is that as the width of that gap increases, the separation between these fringes decreases, and as the wavelength of the light decreases, the separation between the fringes decreases. And we've seen that in the simulation that we've just watched. Let's now look at diffraction gratings. So we've previously looked at a single slit, we've looked at a double slit, and now we're looking at diffraction gratings. And a diffraction grating is where there are many, 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 many slits. We're talking hundreds, thousands. And typically, you are given the number of slits per millimetre. So it might be 300 slits per millimetre. Okay, so if there are 300 per millimetre, that's 300 in 1 millimetre, then we can say 1 millimetre divided by 300 will give you the spacing between them. Here we have a diagram that shows the outcome that you get with a diffraction grating. And we tend to use diffraction gratings with white light. You can use it with monochromatic light. Monochromatic. Mono meaning one, chrome referring to colour, so one colour light. And we get a central white fringe, and then we can see the next fringe over. We have blue in the centre, and then we have red on the outside. Same with the other one, blue nearest the centre and red further out. And on an intensity graph that looks like this, we see that pattern. We see the white light in the centre, in that central maxima, and then the blue is diffracted the least, and the red is diffracted the most within that first maxima. So again, we're talking about n equals 0 and n equals 1, and it's mirrored on the other side. So this would be n equals 2 and n equals 3. And you'll notice that they are following the same pattern, this envelope of decreasing intensity that is mirrored on the other side as well. The equation associated with diffraction gratings is d sine theta equals n lambda. And you need to be able to derive this. So I'm going to show you now. So I'm going to zoom in to two neighbouring slits. Okay. The light approaching these slits will diffract through them, overlap, and arrive at the screen. I'm only interested in where we get the fringes. So if we have a screen over here, we're going to get a maxima on the screen where the path difference between these light rays is a multiple wavelength apart, so n lambda. Remember, if it's half a wavelength out of step, we're going to get destructive interference. We're interested in where we have a whole number of wavelengths path difference, because that will lead to constructive interference. So we're only interested in scenarios where the path difference between these light rays is n lambdas. This diagram is very, very zoomed in because we're talking about a gap that is hundredths of a millimetre small. So on the scale of this diagram, the screen is actually all the way over there in the next city. So the light rays coming out of here we can treat as being parallel. And these parallel light rays, we're going to call the angle between those light rays and the line normal to the grating, we're going to call that angle theta. If we draw this line here, that's a right angle, then this distance here, that's the path difference. And where we get constructive interference, this path difference has to be a multiple of the wavelength of the light. So we know that this distance here is some multiple of lambda. We know by geometry that if this angle here is theta, then this angle here is also theta. And we're going to call the distance between the grating gaps, the slits, we're going to call that d. And all of a sudden, we just have a trigonometric problem. So we have a triangle. It's a right angled triangle here. We have theta. We have the hypotenuse is d. And we have this distance here is some multiple of the wavelength. So if we remember, sine theta is going to be the opposite over the hypotenuse. The hypotenuse we've just called d, and the opposite is going to be n lambda. And that's the equation. You just bring the d up over here, and you have d sine theta is n lambda.